So thank you. Let me say a few words about the JMP Young Researcher Award. So it's an award that we started in the journal. So my name is Jan Philip Soloway, and I'm the editor-in-chief of Journal of Mathematical Physics. And this is the first time that we are giving out this award. So the rules are that you have to be 8 years from your PhD, no more than 8 years from your PhD. I mean, so no older than 8 years from your PhD, and the award is given for a paper published in JMP in the year of the award. So the 2020 award is given for a paper accepted, I should say, in JMP in 2020. Maybe that is actually published in 2021, but it should be accepted in 2020. And the award comes with $3,000 and the opportunity to speak at the next ICMP. So this time we have only one award winner because we have given it out the first time. At the next ICMP, we will have hopefully 3 award winners that will present 3 talks at the next ICMP in 2024. And I mean, there can be more authors on the paper, but the award will be divided among the young, the ones that are eligible authors. If a paper is chosen, it will be divided among the young authors. And the 2020 JMP Young Researcher Award, this is the first installment, as I said, is presented to Andrew Lucas from University of Colorado at Boulder. And I had hoped that Andrew would have been here because we have a nice plaque that he would have been presented with, but now I will send it. I will send it by mail instead. So the award is presented for the paper Non-Perturbative Dynamics of the Operator Size Distribution of the Sachdev-Kitaev model, the SYK model. And in the paper, Andrew studies the spread of information in this model using Lieb-Robinson type bounds, and he relates it to what's called the fast scrambling conjecture. And I believe that in his talk today, Andrew will present further results in the same direction. But congratulations on getting the award. I unfortunately cannot see you, but I believe you are there somewhere, and you will give your talk in a moment.
I'm here.
Congratulations.
You hear me, at least. Thank you.
You're welcome. And I guess we should wait a little bit with the start of the talk because it should start at 3 o'clock. So my presentation here was a little too fast, but I will introduce you, and then we should start at 3 o'clock to give people the chance to come into the room when the talk starts. Okay? What?
Sounds good.
Oh, I'll put it up again. And you should really have had a virtual, you should have beamed Andrew in next to me, but
yeah.
So Andrew, are you in Colorado?
Yeah, I'm just at home right now.
You're at home, right? So it was too bad that you could not make it here, but
yeah, I think in the end I got a bit skittish about, like, I think the EU sort of opened up about a month before this for Americans, and so yeah.
Yeah, no, I really wanted to go to the US, but that's still not possible for Europeans to come to the US. So we're waiting for Biden to make an announcement, but
yeah, they seem to be taking their time.
Well, I guess with the new variant, it's rather uncertain everything. So
Well, that's also true. Yeah. I don't know. I guess I personally would have hoped for a bit more sort of reciprocity and cooperation, but okay.
yeah. We have already done the award. Some people come in, and we are just waiting until 3 o'clock to start Andrew's talk. People that are coming in now look a little surprised. Yes, it's here. Everything was fine. This was Benjamin Schlein who was asking. I'll show it again. Maybe I'll keep standing until so people are coming in for the talk. So, Andrew, I will send you an email to get your mailing address so that I can mail the thing to you.
Sounds good.
I guess we are ready to start. So it's a pleasure to introduce Andrew Lucas. I mentioned already he got the prize, and for what he got the prize, this Young Researcher Award given out by Journal of Mathematical Physics, and this is Andrew's prize lecture, which is related. It's not exactly on the paper, I believe, that you got the prize for, but it's certainly related work. It's on the Frobenius bounds on quantum information spreading. So go ahead, Andrew.
All right, thank you. Yeah, so thank you for the award and for the opportunity to virtually be present at this conference. Today I'll talk a little bit, give kind of a very bird's eye overview of a sort of new perspective on quantum information dynamics that sort of related to, though not equivalent to, sort of classical or classic Lieb-Robinson bounds. Let me just quickly acknowledge many of the people that I've worked with on these topics, in particular my two students, a former student, Shifang Chen, now a grad student at Caltech, and then my current PhD student, Chao Yin. This talk sort of is at heart about understanding speed limits on quantum information dynamics. And the classic version of a speed limit is sort of due to Einstein. In his theory of relativity, right, Einstein pointed out that sort of observers at space-time points that are space-like separated can't talk to each other. There's no way for them to exchange information. And that's because nothing can travel faster than the speed of light. And so roughly speaking, information is also subject to that same requirement. And we can sort of pictorially, draw this very nicely. If I have a little blue dot, which you can maybe, essentially the typical behavior, the typical size of this commutator, but averaged over all states in the Hilbert space. So we're averaging over all psi and psi prime in the formula at the top. After doing that average, we end up with the Frobenius light cone, or we end up with the Frobenius norm. Understanding when this commutator becomes large will give us this notion of Frobenius light cone. The punchline of this talk is that in many theories, with very broad applicability throughout many body physics, these Frobenius light cones can be much stronger than the conventional Lieb-Robinson light cone, and they can often give us insight into new types of physics. So here's a kind of summary slide for this talk. I'm going to sort of give you a bird's eye view of Frobenius bounds and how they've been applied to 3 different systems. At the end of the talk, I'll briefly touch on the latter 2, which include systems with power law interactions, so spin chains, but with sort of more non-local interactions than Lieb and Robinson had considered, albeit very physically relevant. I'll also talk about the Bose-Hubbard model. These 2 were sort of, I think, long-standing challenges in mathematical physics to understand quantum dynamics in. And then the work which I received this award for, and I'll spend a bit more time on, involves the study of operator growth in toy models of quantum gravity. And I'll explain very, very briefly what that comes from. So those are the physical applications of these Frobenius bounds, and I'll kind of quickly summarize and highlight some of the conclusions that we can draw and sort of how this approach to bounding dynamics can give us further information beyond sort of classic Lieb and Robinson bound. On the mathematical side, I think this is a very exciting sort of set of problems because the conventional Lieb-Robinson bounds typically are derived from some type of combinatorial argument at heart. Whereas these Frobenius bounds, Frobenius light cones that I'll talk about, are really naturally understood more in a language of probability theory, using concentration bounds and ideas from sparse random matrix theory and non-commutative analysis. So it's a very complementary approach to, I think, the more widely used one. Anyway, with that said, let me try to briefly introduce this Sachdev-Kataev or SYK model that I won this award discussing. So, okay, this is a model of n interacting Majorana fermions. And really, when I talk about the SYK model, to a mathematician, I'm giving you a random ensemble of Hamiltonians, each of which is defined on the same many-body Hilbert space of dimension 2 to the n over 2. Okay. This random ensemble of Hamiltonians, I'm going to choose it so that up to a normalization constant that we're not going to worry about, but it is said on the slide. These coupling constants Jij are going to be plus or minus 1 up to a normalization constant, chosen IID with probability 1/2 for each sign. And our goal is to show that this trace of an anti-commutator of fermions squared, so psi1 evolve with time and then anti-commute with psi2, properly normalized. Our goal is to show that this has this very peculiar 1 over n times e to the lambda t behavior. Here n denotes the number of fermions in the system. Lambda is intended to be an order 1 constant. That's our goal, to show that that is indeed the case. And we'd like this behavior to hold until the right-hand side of this inequality becomes order 1, or the time scale is logarithmic in n, the number of fermions in the system. So this is mathematically the setup of this problem. The anti-commutator here is just because we're dealing with fermions, but if you're not used to thinking about that, it's really going to be analogous to the usual commutator in a Lieb-Robinson bound. Okay, just a little different for these operators. So let me try to say at least a couple words about why we're studying this problem in the first place. So this exponential growth is believed to be a many-body quantum mechanical manifestation of the butterfly effect that's well known in classical chaos. And on the next slide, I'll try to give a little more intuition as to why that's not an unreasonable analogy. The butterfly effect coming from classical chaos, right, says that if I have a classically chaotic system and I just perturb by a small amount epsilon the initial condition of that system, after time evolving, the 2 trajectories will begin to exponentially deviate in time. The exponent lambda, which is not accidentally labeled similarly to the one from before, this is a Lyapunov exponent, which tells us how much 2 trajectories will deviate over time. Now, if I were studying a conventional sort of discrete finite dimensional Hilbert space spin chain, like Lieb and Robinson studied, you would not be able to see this exponential deviation essentially due to the granularity of the local Hilbert space. The Lieb-Robinson bounds would essentially tell us that rather than exponential deviation, we're going to at best see something that looks kind of polynomial. But for this SYK model, because there's no spatial locality, we just have all fermions talking to each other via the Hamiltonian, it's possible, as I'll mention, to genuinely see this kind of exponential growth. And this relates to gravity. I'll say just a few words. It relates to gravity because we believe via something called ADS-CFT, or the gauge gravity duality conjecture, that this exponential growth is related in some sense to the way in which particles on a gravitational side of this duality fall towards a black hole horizon. So this quantum mechanical model is going to be dual to a two-dimensional theory of quantum gravity. And the physics that we're studying here is in some sense linked to the behavior of particles as they fall towards the black hole horizon. And the idea that this kind of exponential growth is the fastest possible in nature is called the fast scrambling conjecture. Okay. So to try and understand this exponential from maybe a slightly more microscopic perspective, we can think about looking at this psi1 of t, this time-evolving operator, rather than just sort of writing this abstract psi1 of t. Let's imagine that we actually wanted to calculate what it is. So a convenient way we could do this calculation would be to fix a basis for all possible operators it can evolve into. In this model, that's just going to be all possible products of Majorana fermions. And let's just say these Ci, Cij, et cetera coefficients, these just tell us, they're essentially basis elements, okay? So psi1 of t is evolving in this vector space of all possible operators, and we're just keeping track of the overlap with each basis operator, okay? And very much an analogy to usual quantum mechanics, in this operator Hilbert space, to use the loose physicsy jargon here, we can say the probability that an operator has size s, we can formally define this to be the sum of squares of all of the C coefficients that come with a string of fermions that has size s. So I guess the IQ should be IS here. Okay. And what I claim is that the origin of this exponential growth in the anti-commutator that I showed before, that exponential growth is going to arise from the fact that as this operator psi1 evolves in time, it's going to evolve into strings of more and more fermions, okay? And I claim that in some sense, most of this operator will have about e to the lambda t fermions in it at time t. That's why I have this exponential anti-commutator growth. Now, the physics argument for this exponential growth is coming from the observation that if I start with a single fermion and I commute once with the Hamiltonian, then I would get, in this case, q minus 1 fermions. Okay, so if I started with psi1, now I have psi2 through psi-q. That would come if I commuted psi1 with the Hamiltonian coupling the first q fermions. Now, when I get to this step, I have q minus 1 different choices. I can sort of commute to either try to get rid of psi2 or psi3 and so on, okay? And for each possible choice, right, I have a different operator. And so you could crudely say, well, I've got, q minus 1 different choices, and the number of choices that I have for how to next grow the operator is growing linearly with the number of fermions I have. So this sort of feels like a classic infection process that we're all a little too familiar with. And that was really the analogy that was used when the string theorists were studying chaos and operator growth in this model. Okay, this is not quite rigorous though, and one of my goals was to try and put some more serious backing behind some of these claims. Now, if we tried to approach this problem using a sort of typical Lieb-Robinson bound, you might originally take objection to the fact that this model has no spatial locality, but actually that's not too horrible. One can talk about Lieb-Robinson bounds for particles interacting on graphs, and the complete graph is sort of a reasonable choice to consider. But the problem with the Lieb-Robinson bounds is that, as I mentioned earlier, these bounds typically are derived by combinatorial arguments. So the way they'll go is that I look at, in a little time step, dt, how much does my operator change? Using the triangle inequality, I bound the operator norm of this little change to the operator. And sort of using this, this change, I'll try to sort of build up via some combinatorial arguments, a set of constraints on each of my anti-commutators. The problem in this model is that randomness is really important. And if we don't average over this whole random ensemble, right, we're going to lose all of these plus or minus signs. And if you add up sort of the number of combinatorial terms in this system, you'll find that it grows way too quickly with n, and we get a bound on the Lyapunov exponent that scales as n to q over 2 minus 1, something like that. So here it's actually more natural to proceed in this sort of physicsy language that I mentioned before. We want to think of psi1 of t as really like a vector that's evolving in its own quote unquote Hilbert space. This is really just a finite dimensional vector space though, right? So psi1 of t is effectively rotating in this high dimensional space. And the question that we're asking is, what is the expectation value of a certain so-called super operator size on this operator wave function? And a little more precisely, if we want more fine-grained information, we can ask, what's the probability that we have size s? This is essentially the length of this vector projected onto a certain subspace. Okay, we can ask what this probability is. The unitarity of quantum mechanics says that this is genuinely a well-defined, sensible, normalized probability distribution. And so the question that I'm going to address is, how can we constrain the dynamics of this probability distribution? The way that we do this is by recasting the many-body Schrodinger equation. You can formally and somewhat straightforwardly just cast this as essentially a differential equation for the probabilities Ps of t. This is not, you don't get this for free. The price you have to pay when you try to go from the many-body problem to effectively a one-dimensional problem is that you started with a time-independent Hamiltonian, and you can get an auxiliary problem, but with totally uncomputable time-dependent coefficients. However, it turns out these time-dependent coefficients are bounded. They can be bounded essentially by the operator norm of what's called the Liouvillean, or commutation with h, sort of projected onto different size subspaces. And because the Hamiltonian only talks to q fermions at a time, we know that this K matrix is sort of local. It can only jump you by size q minus 2 at the most, okay? And so actually this part of my derivation was fairly simple. We just convert the many-body problem to this 1D problem. We know it's sort of local, and the hard part is now to actually constrain these transition rates to try and prove the fast scrambling conjecture. So this part's very technical, and I don't want to bore anyone with too much about it. But suffice it to say that it's achievable using concentration bounds. We can bound this KSS of t, and it turns out that almost surely it will scale as some constant times the size of the operators. And remember, S and S prime never differ by too much. This scaling comes about due to constructive interference between growing operators. So I'd like to comment that this is not quite a sort of classical infection type picture. If this were sort of entirely classical and incoherent dynamics, you would expect that sort of different contributions just add sort of orthogonally. But to actually achieve this S-dependent scaling, you really need operators to constructively interfere with each other as they grow. And a simple picture for how this happens is that I've got a big string of fermions. And so here, this is sort of schematically denoted with 4 lines, sort of in a Feynman diagrammatic story. And I can either commute with the top fermion or the bottom one, and that gives me this little green or red arc in my diagram. I can do those commutators in either order, though, and so they'll constructively interfere with each other at intermediate steps. Okay, anyway, the hard part of this calculation is accounting for this effect, but not sort of over-accounting for it. At the end of the day, we can use these bounds on our transition rates in this auxiliary 1D block, and we can prove the fast scrambling conjecture that the operator size, the average operator size in this problem can only grow exponentially with time, up before, of course, times that scale is log n. Okay, so that was the SYK model. Let me very briefly talk about some other applications of these Frobenius bounds, and then I'll wrap up. So, as I mentioned earlier briefly, one interesting application of these ideas is to spin chains that have power law interactions. So if we have power law interactions, this, in this toy example, amounts to a Hamiltonian where I have, let's say, Pauli Z couplings that decay off as 1 over the distance, this is I minus j here on a 1D lattice, to the alpha power. If you look at the Frobenius the operator norm of a commutator in this system, you find that for exponents in 1D, alpha above 3, there's a finite velocity at which this commutator can grow large. So this is just like the classical Lieb-Robinson theorem in this case. If you get below exponent alpha equals 3, in between 2 and 3, essentially the velocity grows algebraically with time, and then below 2 exponentially with time, sort of all hell breaks loose. But it turns out for the Frobenius norm, the exponent essentially gets shifted down by 1. So when your alpha is 2 plus epsilon, you effectively have a finite velocity of information in a typical state, even if in special states you can find that information almost travels exponentially quickly. This tells us that Lieb-Robinson bounds are very weak in typical states in these systems with power law interactions, and it demonstrates that there's really a hierarchy of different notions of information spreading that we can talk about. We can apply these Frobenius bounds to the Bose-Hubbard model and similar models of interacting bosons. In this case, there's a formally infinite dimensional Hilbert space, and we can regulate this by sort of defining a clever type of inner product on our quote unquote operator Hilbert space. This regulator effectively amounts to restricting our study to states that have a finite number density of bosons in the thermodynamic limit. And we can show that in this family of states, there is a finite velocity at which this commutator of bosonic operators can grow. So even though this is a formally infinite dimensional Hilbert space and a formal Lieb-Robinson bound could not exist because you genuinely can find very high density states where information propagates arbitrarily fast, this tells you that in physical states, that an experimentalist is going to study, there is a speed limit on information. All right, so just to summarize, I've introduced this notion of a Frobenius-like cone that cares not about worst case behavior, but about the typical size of commutators over some ensemble of states. And I've highlighted applications of this idea to a broad array of different problems within mathematical physics. And I think this is sort of a really exciting direction in this little area of the field. There are a lot of problems that remain open, both sort of on the physical side and on the mathematical side. So that's all I wanted to say. Thank you again for the award, and happy to answer any questions. Thanks.
So thanks a lot for a nice overview of this work that you have done on these bounds. Are there any questions from the audience in the room? I actually had one question on the Bose-Hubbard model. So do you know in what sense this bound you have is optimal? Or, I mean, so we know that the usual Lieb-Robinson bounds will not hold, and we have some counterexamples, but you know how close these counterexamples get to the bound you have? I mean, in what sense it's optimal?
So I'm not sure what counterexamples you have in mind. There are models where you say that information can spread exponentially quickly with time. In these models, they violate the assumptions that would go into our bound, so we also can't say anything about them. What we can say is that the velocity of information sort of, it basically can grow linearly with the density. And that does match scaling that's been seen in numerics and from sort of analytical arguments in certain types of Bose-Hubbard models. We're off by about 2 orders of magnitude in the prefactor of that coefficient, but it does have the right scaling. So that's sort of in the last equation on this slide. So we think that qualitatively the bound that we have cannot be improved, but yeah, maybe you can try to reduce our velocity by a factor of 100.
Sorry, and where was the factor of 2? You said you were off by a factor of 2 in the orders of what?
Oh, sorry, these coefficients C1 and C2 in this inequality are about 100 times larger than they are in at least one physicist's sort of toy model of how you get this density-dependent velocity. But this is, I think, just because we got kind of lazy once we got the right asymptotic scaling. Yeah. But yeah, I mean, when we go beyond the Bose-Hubbard model, our bounds get a lot weaker. I mean, we can sort of make the interactions a little bit more non-local. That starts to change the density dependence here, et cetera. So probably there is some room for improvement, but I think for the Bose-Hubbard model, the improvement is only quantitative.
Thank you. Are there any other questions from the room? Are there any questions online? Doesn't seem to be the case. So Andrew, thanks a lot for a nice lecture and congratulations on the prize.
Thank you.